There's actually good reason for universities to pay attention to this favored, neglected language. Now, it turns out JavaScript is the most popular programming language in the world. There are more people writing in JavaScript today than any other language. That is not why this should be of interest to you, but it is an interesting fact. Now, you could argue that most of the people who are writing in JavaScript should not be writing in any language. And I'm not going to debate that point tonight. That's interesting. So while JavaScript is the most popular language, at the same time, it is the most unpopular programming language. This is in the sense where if you were to take a survey of any group of programmers, ask the question, what language do you hate the most? By far, the most common answer is going to be JavaScript. And that will be including people who have never used it and people who use it every day. So it's remarkable that a language could be so popular and unpopular at the same time. One of the reasons why the people who use it hate it is because they don't bother to learn it first. That's the first mistake most people make with JavaScript. I made that mistake with JavaScript. It looks so familiar that you think, I can just pick this up. And in fact, you might be resentful that people don't have to be using this language. So just to show them, whoever they are, I'm not going to learn it. Like that's going to make any difference. That turns out to be a really bad practice. Programming is very complicated stuff, and programming in ignorance is crazy. You would not do that in any other language, but for some reason people feel good about being ignorant about JavaScript. Some evidence that JavaScript is actually a good language is that it is succeeding very well in an environment where Java was a complete failure. The Java community doesn't like to remember this, but Java applets were the biggest failure in the history of software engineering. Java applets were poised to rule the world, and they fell on their face hard and flat. JavaScript is succeeding there, doing the very thing that Java failed so badly to do. So JavaScript is not succeeding simply because it's the language of the browser, because Java was the first language of the browser. JavaScript is succeeding because somehow it got something right. And it got it right because of this guy. This is Brendan Eich. It's his fault. He invented JavaScript. He was a kernel hacker at Silicon Graphics. He was interviewed by Netscape to add HyperCard-like functionality to the Navigator browser. Now, Brendan had no experience with HyperCard or with scripting systems, but he was interested in programming languages. In fact, he was thinking about writing a scheme interpreter. And he brought this up in the interview, and he suggested that Scheme might be a good language for their HyperCard kind of extension to the Navigator. And they thought, wow, this guy's really smart, and so they hired him. Now, just before he started work at Netscape, somebody at Netscape found out what Scheme was. So on his first day of work, they said, no, you can't do Scheme. Make it look like Visual Basic or Java, something people like. People don't like Scheme, don't do Scheme. So he threw out his design and created a new design and implemented it in 10 days, which is an insanely short period of time in which to develop and ship a programming language. And Netscape shipped the language pretty much as is, without having tested it, without having any evidence that, in fact, the language was useful. An appallingly bad piece of management at Netscape, which is why there's no longer Netscape. And it's also why JavaScript has lots and lots of bad parts. It probably has more bad parts per ounce than any other programming language. But it also has some good parts, and that's why I'm here. That's why I think JavaScript is deserving of your interest, and I'll try to justify this claim as we go on. But first, JavaScript has a double equal operator, which unfortunately does type coercion on its arguments before it does a comparison, and so it gets false positives. There are actually very specific rules that govern this, but looking at this, it looks pretty random. In fact, most people who are using the language could not tell you what the rules are, which determines how double equals works. Fortunately, there's a triple equal operator, which returns false for all of these comparisons. So it does the right thing. It returns true only if the two things have the same type and the same value, which is what you would expect. So I would consider that a good part. because it always works predictably. I consider this a bad part because it doesn't. So this leads to an interesting principle: never use the bad part. There's no reason to. There's no compelling advantage to using this form. In fact, there's some serious disadvantages. The other form is free of those disadvantages. So by simply ignoring this bad part of the language, you make the language a little bit better. You have the power to improve it. I consider this an awful part. So can anybody predict what the value of C is going to be? Anybody? Yeah, it's $12. Anybody surprised with this outcome? The reason for this is that it uses plus to do both concatenation and addition. And so there are cases where you think you're going to add and instead you concatenate. This is a very common source of errors. And unfortunately, there's no alternative to this. Plus is the only way of doing addition in this language. So you have to be really careful when you intend to add that both of your operands are numbers. I consider this an awful part, and this is something that you cannot remove from the language, unfortunately. So why haven't the bad parts been fixed? I mean, the language has been out for over 15 years. There are some reasons for that. One is the nature of the web. When you're making applications on the web, there's an expectation that your programs are going to run on every web browser that has ever shipped. In most other environments, like in the desktop or in server applications or embedded applications, you've got more control over what version of the language and what, even what brand or revision of the language you can use. You don't get that on the web. You're expected to run with everything. And since IE6 is still a dominant web browser and it's over 10 years old, you have to run on something that is that old. And so once a bug gets into the web, it's really hard to get it out. Another problem is that the language has lots of bad parts, but the bad parts are not useless. I would never say that the bad parts are useless. They're just dangerous. They're just buggy. And there's some people who have very cleverly found uses for all of these bad parts. And if we removed these bad parts from the language, those programs would break. Now, you could argue that those programs deserve to break, and again, I'm not going to argue that. But we're trying not to break the web. We're trying to keep the web stable. So we're stuck with all this badness. But the good news is that the bad parts can be avoided, and the good parts are really, really good. And it's because of those good parts that I'm here today. So to explain where the bad or where the good parts came from, we're going to go through a little bit of history. We're going to start for the language was LiveScript. Now at that time, in late 1995, Netscape was a hugely popular company. And the reason for that was that they had declared that the web browser was going to be the thing that was going to liberate us from Microsoft. That if we wrote all of our applications to be delivered by the browser rather than by the operating system, then it didn't matter what the operating system was, and at last we would be liberated. And as a consequence of that, interest in Netscape went through the roof. At the same time, Sun had made the same claims about Java. They said if you write your applications to the Java VM instead of the operating system, again, we can be liberated from Microsoft. Netscape and Sun were only a few miles away from each other, and they realized that they needed to work together, because if they didn't, Microsoft would play them off against each other, and they would both lose. So they formed an alliance, and the first thing they decided was that Java would be added to the Netscape browser. The second thing they were going to decide was that Netscape would have to kill LiveScript. Anyway, that's what Sun determined. Netscape didn't agree with that for a couple of reasons. One was, while they got Java into the browser, it wasn't well integrated. It couldn't really talk to the page. Only LiveScript could talk to the page. They set it up so that LiveScript could talk to Java, but if they took LiveScript off, then Java couldn't interact with the rest of the browser experience, and that would look kind of stupid. But the bigger reason was that they still believed in a novice programming market. They wanted to make the browser something that could be programmed by beginners. And beginners cannot deal with Java. A beginner cannot write Hello World in Java. It's too complicated. Whereas Hello World in JavaScript, or LiveScript as they called it at the time, is trivial. So there was an impasse, and the relationship between the two companies almost broke down when Mark Andreessen, the founder of Netscape, maybe as a joke, suggested that they change the name of the language to JavaScript. And that they intentionally go out and misrepresent the relationship between the two languages. They went out and said that JavaScript was Java's stupid little brother. It wasn't a different language, it was the same language dumbed down a lot. People believe that that's true, and it turns out it was never true. The languages do not have that kind of relationship. Now, through all of this, Microsoft was kind of alarmed that these two companies in California were getting ready to destroy Microsoft. And so they thought they should pay attention to this browser thing. Up until this point, Microsoft thought the future of communications was going to be fax. So this web thing coincided. So they went out and bought a browser, and they decided to reverse engineer JavaScript. And they did the best job of reverse engineering in the history of the company. Still unmatched. They found every bug, every design defect, every error, carefully documented it, and replicated it. Had they not done such a good job of that, we would not be talking about JavaScript today. They called their thing JScript. The reason they called it JScript was because Sun claimed ownership of the JavaScript trademark. At that time, Sun thought they owned all uses of Java. They were even shaking down coffee companies, accusing them of trademark violations. This is true. So at this point, Netscape was alarmed. They thought, oh no, we're going to be embraced and extended. We're going to lose our nice little language. It will become a Microsoft thing. So they decided they needed to make a standard. So they went to the W3C, which is the steward of the web standards, and said, we've developed this language for the web. We'd like you to standardize it. Now, it turns out W3C had been waiting a long time for a chance to tell Netscape to go to hell. So they told Netscape to go to hell. So W3C has never had any involvement with JavaScript. So they shopped around for another standards body they considered ISO, and eventually ended up at the European Computer Manufacturers Association, ECMA, which is a long way to go for a California software company, but that's where they ended up. And they asked ECMA if they would make a standard for them, and ECMA said, okay, sure. And but one condition, you cannot call the standard JavaScript, because JavaScript is a Sun trademark, and we have an exclusive license to use the trademark, so you can't call it that. Now, at that point, ECMA should have told them to go to hell, but they didn't. Instead, they convened a committee, and they started working on it. In fact, Microsoft joined the committee, and Microsoft made two significant contributions to it. One was they took their log of their reverse engineering log, all the notes that they'd used for creating JScript, finding all of those bugs, and they contributed that to ECMA, so that became the standard. And the other thing they did was they insisted that all of those bugs and defects and design errors that they found remain in the standard. And they're still there. So quality was not a concern in the design, implementation, or standardization of this language. And that's why the density of bad parts is so extremely high. The other thing the committee had to do was figure out what to call it, since they couldn't call it JavaScript. And they kicked around names like WebScript and NetScript, but they couldn't agree. So in the end, they published it with the working title, as often happens. In this case, it was ECMAScript, which is maybe the worst name in the history of programming languages. But that's what it's called. So the question comes up, well, what should we call it today? ECMAScript is the only free and clear name we have, because JavaScript now belongs to Oracle Corporation. So some people think one of the bad parts of JavaScript is that it doesn't have an int type, but I think this is actually a good part. If you look at what ints actually do in most programming languages, say we've got A and B, which are both greater than 0, it's possible to add them together and get a result which is smaller than A or B, which is insane. how can you have any confidence in the correctness of anything that you're doing when this kind of crazy shit is going on in your basic numbers? And if you can't count on your numbers, what have you got? JavaScript does not have this bug in it, which I think is a good thing. So, in fact, integer arithmetic in JavaScript is exact up to 9 quadrillion or so. Once you get above 9 quadrillion, things start to get a little fuzzy, but at least they don't go negative on you. So if you add 1 to a number that's significantly bigger than 9 quadrillion, 1 acts a lot like 0. You can't tell the difference. But 9 quadrillion is pretty big. It's still big enough that you can represent the national debt. Hopefully we're not going to push the limits here. Okay, so another good part of JavaScript, there's only one number type, and that's binary floating, which is the wrong type, but it's the one we've got. The reason having one number type is good is because if you have 2 or more, then there's a chance that you're going to pick the wrong type and introduce bugs as a result of that incorrect decision. That's a bug you cannot make in this language. So that actually turns out to be a good thing. The bad thing is that it's based on IEEE 754 government. Now, it turns out every programming language designed in the last 20 years contains the same defect. And let me show you why I think it's a defect. So this is the most commonly reported bug in the Mozilla database, which is some variation on 0.2 plus 0.3 is not exactly, or 0.1 plus 0.2 is not exactly equal to 0.3. Which is only a problem if you're on a planet that uses the decimal system. But that would include ours. And in particular, money. And all the currencies of the world are represented with decimal fractions. And when you're adding up people's money, they have a reasonable expectation you're going to get the right sum. And you don't, because in binary floating point, you cannot exactly represent the decimal fractions. And so that's a hazard, and that's why it's the most reported bug. It's not a bug in the language unless you consider having picked the wrong number type to have a bug. So this is the beast. And the reason for our troubles here is this 2. If this had been 10, everything would have worked out fine, but it didn't, and so we're stuck with that. Back in the 50s, that 2 made a lot of sense because it made the hardware cheaper to build. Today it's irrelevant, but we're still stuck with that factor. Binary floating point is good for things like chemistry or physics, where you've got extremely large and extremely small values. But for what we do in the web, certainly, for most applications, we're not in that range. And so this really doesn't fit for the things that we do. So it just shows again, just because something is a standard doesn't mean it's the right choice for every application. When will we learn? I don't know. Okay, so a mathematician might complain that this is a bad part of JavaScript. This is one of the ways in which you can add 1 to a number. And they go, well, that's mathematical nonsense. That doesn't make any sense. Why would we write assignment statements that way? And there's some languages where you don't, where they use an operator other than the equality operator for indicating that. But it turns out when you've got binary floating point, there are actually a lot of values that make this a true equation. So here are a few of them. One of them is infinity. We have a value called infinity. You add 1 to infinity, you get infinity. We have something called max value. You would think that if you added 1 to max value, you get infinity, but you don't, because you get an underflow, and so the precision goes away, so you get max value again. And basically that's true for any number that's bigger than 9 quadrillion. One surprising case is there's something called nan, which stands for not a number, even though it is a number. And it turns out that nan plus 1 is nan, but this equation fails because nan is not equal to itself, which is this insanely stupid idea. How can a thing not be equal to itself? In fact, even stupider than that is nan not equal nan is true. Again, IEEE floating point. It's appalling. Okay, so happier news now. We've got strings. A string is a sequence of Unicode characters. We've got two literal forms for writing strings, double quotes and single quotes. And I recommend specializing it. So use double quotes for strings that are used outside of the program, that might be exported or shown to users or something like that. And use single quote for strings that are internal to the program. I think that just makes it a little easier to follow what's going on. Strings are immutable, which is a good thing. It means that once a string is made, you can't go into the middle of it and replace characters. Any two strings that contain the same characters in the same order are going to be equal. So cat and the concatenation of C, A, and T are equal, which is great. Java got this wrong. JavaScript got it right, being the superior language. A new bad part that just got added in the 5th edition of the language, we now have string literal continuation. So if you have a string that's too long to write on one line, you can put a backslash at the end and continue it on the next one. The reason I think this is a bad part, two reasons. First, it screws up indentation because the continuation has to start over at the margin. And indentation is so important to making programs readable. Having stuff that mucks it up, I think, actually works against us. But the bigger problem is, this case here where we got the syntax error. Can anybody see why the second one is a syntax error? Yeah, there's a space right there. See? I mean, it's obvious once it's pointed out. So mostly we should be concerned with bug avoidance, because bugs are terrible and work against us. So anything we can do to reduce the number of bugs we're going to encounter in our careers is a good thing. And so avoiding forms where you cannot easily tell, is this correct or not, is a good thing. I don't want to be using forms that I cannot distinguish from common errors. So I wouldn't use this. There are at least two other ways in the language for dealing with long strings. This is unnecessary, so I consider it's just not worth the cost. We've got two booleans in this language, and we'll be happy to know that they're true and false. No problems there. And we have objects. Okay, we're starting to get to some good stuff now. So an object in JavaScript is a container of key value pairs. The key can be a string. That's unfortunate. It would have been better if a key could have been any value, including other objects, but we didn't get that. But values can be any value, so that's good. So you can deeply nest objects, you can build graphs out of objects, you can do good stuff. And there are two bits of syntax for manipulating the properties of objects. You can use the dot notation, or you can use the subscript notation. And the two are pretty much equivalent, at least in the case where the key is an identifier. We use prototypal inheritance or delegation in this language. So when an object is created, it delegates to another object. And so if you try to get a property from the first object, it'll go to the thing that it delegates to. We call that delegation. We also call it differential inheritance. And that you make a new object and you just change it with material that makes it different or distinct from the object that it inherits from. And this turns out to be really easy. It's so much easier than the classical program. You make an object that you like, you create new instances that inherit from it, you differentiate those new instances, and that's it. No taxonomy, no classification. It's a superior programming model. For a long time we were told that this was sort of a throwback. It wasn't even object-oriented. But that's not true. This is actually a more evolved programming model than the classical model that we see in the other languages. We have function expressions. This is the lambda. This is the thing that produces a function object as a result. Functions are first class in this language. That means that you can take a function and you can store it in any variable. You can store it in a property of an object or store them in arrays. You can pass them to other functions as arguments. And best of all, you can return them as return values from functions. That allows you to do high order programming of these things, which is amazing. And functions are objects in the way that objects are used in this language. So they can inherit. So functions have methods. It turns out. We have a var statement, which is used to declare and possibly initialize variables in this language within functions. You don't specify types when you declare a variable because it's a loosely typed language, so any value can go into any variable. One thing to watch out for is that if a variable is declared anywhere within a function, it is visible everywhere within the function. So we don't have block scope in this language, we only have function scope. Now it turns out function scope is sufficient for writing good programs. You don't need block scope. But the language syntax looks like promises that you have block scope, and it doesn't. And so if you come into this language using conventions that expect block scope, you're probably going to have errors. So because of that, my advice with using the var statement is always explicitly declare all of your variables at the top of the function. In a block scope language, the best advice is declare them in the innermost block that are used, probably at the site of first use. That turns out to be extremely bad advice in a block scope language, or in a function scope language. So want to see some JavaScript? Okay, so here's a program called digit name. Digit name takes a number and returns a string. And it gets the string from a global variable called name. And what we're assigning to names is an array containing a bunch of strings. Now, there's a problem with this program in that it depends on a global variable. It turns out global variables are evil. There are big reliability hazards with them, because if there's something else loaded with my program that uses a global variable called names, we're going to conflict. And either this code's going to fail or that code's going to fail, and maybe we both fail. And this is something you cannot test for, especially in the web, because you cannot predict all of the code you're ever going to have to run with. It's especially true in applications that might have advertising on them. Some of the worst script you've ever seen in the world comes with ads. And your program has to work with whatever comes down the chute. So the only defense against this is to avoid using global variables. And the language provides a couple of ways of doing that. So here's another way of writing this function. Now I'm assigning to digit names a function that has a private variable called names. We have function scope, so names is no longer visible to the outside. So that's good. So this solves my global variable problem for names. The problem with this code is that every time I call this function, I'm going to build an array, put 10 strings in it so it can extract 1. That's really inefficient. Now, an optimizing compiler might recognize that names is invariant over invocations, and so could try to optimize that out. But optimizing compilers could take several minutes to do their work, and web applications want to start running immediately. So JavaScript compilers do not do that optimization, probably never will. So we have to do that optimization ourselves. So here's another way we can write it. Again, I've got a function, and it's got a variable called names, which we initialized like before. But this time, instead of returning a value, it's returning a function. And that function is going to return an element from names. Okay? And the outer function, I'm invoking immediately. Okay, so what I'm assigning to digit name is not the outer function, it's the outer function's result. The outer function's result is this green function here. And because of a property called closure, this inner function will continue to have access to the outer function's variables even after the outer function has returned. So when we call digit name here, or actually when we assign to digit name, the outer function returned immediately after we called it. Okay, so at this point, the outer function is finished. The inner function is now stored in digit name. We call it. It looks up names. It still has access to this name. It doesn't have a copy of this guy. This guy's scope, its context, is still alive as long as the child function needs it. This is called closure. This is the most important idea in JavaScript. This is the most important idea in the history of programming languages. This is the thing that Brendan Eich took from didn't tell anybody. He just kind of snuck it into the programming language because it was cool. And people came along years later and discovered it. Yeah. This is the source of most of the expressive power in JavaScript. This is the really important idea. If you remember only one thing from my ranting tonight, this is it. This is the powerful idea, that you can have a function that's returned from a function, and the function that's returned closes over the variables of the function in which it was created. Everybody still with me? No blank looks anyway. All right, good. So this is a wilder example. This is a memoizer. Let's see, how to break this down. Okay, so memoizer is a very simple function. It takes a memo array and a function called a formula, and it creates a variable called recur, which is a function which it returns. Okay, so that's pretty simple. So let's call memoizer. We'll pass it an array of initial values, in this case 1 and 1, and we'll pass it a function for computing other values that are not yet in the memo. So the formula for factorial is n times the recurrence of the factorial function of n minus 1. Okay, so when we call recur, if we're calling it for a value we've already seen, we'll simply get a value out of the memo array, and it will be defined, so we can simply return it. But if we're asking for a value we haven't seen yet, it will call the formula that was passed, passing in itself so that the formula can recur, and the argument that it needs to do that. So by doing this, you get memoization of functions so that only the first time you call for a particular value, you actually have to do the work. Now for something like factorial, there's not much of a win. But for something like Fibonacci, this is a huge win, because Fibonacci gets explosive. It recurs at n minus 1 plus n minus 2. So you get recurring going off. It gets hugely explosive, but it runs in linear time if you run it through the memoizer. So this is an example of using functions to help us to write functions. That's when you're using the language expressively. You remember digit name that we looked at before? We can get the same result. We can simply pass the array of strings to memoizer, and we're done. We didn't even have to write the digit name function. It writes it for us. We just had to tell it what the answers were.